Okay, today we're going to have a look at how we go about calculating the empirical formula for magnesium oxide in the lab. So practically speaking, so presumably you've already watched this video before, and I'm just going to skip through just important parts of it, but all he's doing is just going to put some ceramic heat-proof blocks on a scale, okay? He's gone out and weighed a whole bunch of magnesium, okay? So that magnesium, which is in a crucible right now, so he's obviously tared that before, we're just going to write the mass of magnesium that he started with is 0.33 grams. Notice that our scale is limited to two significant figures here. Oh, not two significant figures, I should say two decimal places here. Okay, so it can only measure to probably plus or minus half of the last significant figure. So it's 0.335 or 0.325, you can assume. Moving on, he now puts the magnesium it's in a crucible, sitting on a pipe clay triangle, sitting within a ring clamp, and he's going to heat it, okay? And when he heats it, what's going to happen is the inside of the crucible, we're going to hope that this magnesium reacts with the oxygen inside of the crucible to form magnesium oxide, okay? So I'm just going to write this as a word equation now. So the magnesium plus oxygen presumably goes and forms magnesium oxide. Okay, so the reaction proceeds. He heats it with his Bunsen burner. It gets pretty hot. Okay, and he's going to lift the lid up at various times just to check the reaction progress. But also, it's really important that you're letting oxygen in there. Otherwise, you're going to have oxygen as your limiting reagent, where you actually really need it in excess. Okay, remember we talked about that last time. So we don't want the amount of magnesium oxide formed to rely on the amount of oxygen. We want it to rely on the amount of magnesium because that's the mass that we know. We know this mass. We don't know the mass of oxygen that reacts. It's a little bit difficult. We know this more accurately. So the reaction proceeds, and eventually what you're left with is a white powder, okay, which we're going to assume is magnesium oxide. Okay, so there he is weighing it there, and it weighs 0.49. So the mass of, I'm just going to write it in words here because we don't know the formula yet. The mass of magnesium oxide equals 0.49 grams. Okay, we can actually deduce from that now, and we're making a large assumption here that the mass of oxygen, okay, is equal to that 0.49 grams, and we subtract the initial 0.33. So we're assuming that any mass added between here and here is actually due to this oxygen. So I'll write it down here just so you can see. That's 0.33 grams. This is 0.49 minus 0.33 grams. And this is 0.49 grams, okay? Just so to make sure mass is conserved. And all of these things so far add up. Now, to calculate that empirical formula, what we need to do is we need to go about calculating the number of moles for each of these. So let's go ahead and do that. My number of moles of magnesium here is equal to mass on molar mass, okay, which is equal to 0.33 grams divided by now my molar mass of magnesium. I think it's 24.35, but let's just check that on our data sheet. Don't assume anything ever. 24.31, close. 24.31 grams per mole. Okay, I'm going to stick that into my calculator, and the number of moles of magnesium that we get is 0.33 divided by 24.31. We get 0.01357466063 moles, okay, because grams and grams cancel, divide by inverse moles, you get moles. Okay, I'm going to now calculate my number of moles of oxygen, okay. Notice I'm just going to write that it's an O. I don't know, I don't really know what's going on here. I just want to know that the number of moles of oxygen that I have in total, not as O2, because we want to know in the final product how many oxygens there are. It's a really common mistake that people will write this as O2. So the number of moles of oxygen are 0.49 minus 0.33. It's equals 0.16. So I've got 0.16 grams presumably, okay, divided by 16.00. Remember, this is in grams per mole. Remember, it is not, and it would be incorrect to assume that it's 2 times 16.00 grams per mole. This is assuming O2, and it is completely wrong. We're not talking about O2 here. We're actually talking about, of course it reacts as O2, but what we're looking for, again, just to remind you, and I'll write it up here, we're looking for the ratio between magnesium and oxygen in magnesium oxide. So we're saying, what's this and what's this number here, okay? Is it a 1-to-1? Is it a 1-to-2? We don't know. So we're not looking at oxygen. We don't really care about that for now, okay? So if I do 0.16 divided by 16, I get 0.01 exactly, okay? And once again, that's in moles. Okay, now what I need to do, you can actually already look at this a little bit and you can kind of see where this is going. I need to take a ratio of these. So the number of moles of magnesium divided by the number of moles of oxygen is equal to 0.01357466063 moles divided by 0.01. Okay, if we divide this by 0.01, it's the same as multiplying it by 100, and essentially what we get is we actually get 1.357466063. Now, this is a little bit weird, right? Because we're saying that there's 1.3 times more magnesium, okay, than there is oxygen here, which we actually know not to be true. We actually know that that the formula for magnesium oxide is in fact MgO. We know that, so there's actually something going wrong here. What I want to talk about a little bit in the next video is why that's going to be wrong. But just to finish this one off, if you have a third more magnesium than you have oxygen, okay, it's roughly, 1.3 to 1, and you can kind of consider this to be 4 parts to 3 if you consider every third. So this is really 4/3. This is roughly equal to 4/3, which means that oxygen would be 3/3 being 1. So we would get this formula of Mg4O3. I'll just move the camera to see that. That's what we would get from this, but this is actually incorrect. We know that. So in the next video, we're going to talk about why.